right. So thank you all for joining the fourth and final Hypersystem seminar in this series today. So this is a part of a series of 4 seminars that were taking place this semester, and this is the last installment today. So today we'll be hearing from Youssef. Youssef Ait Si is a PhD student working with Dr. Adnan Saoud in the College of Computing Department at the University Mohammed VI Polytechnic since October 2022. So before that, he was a data scientist / engineer at the company Atos in France for about a year, where he obtained strong programming skills and sharpened his ML knowledge. He received his general engineering degree from École Centrale Casablanca in Morocco in 2020, where he was chosen in his last year of graduation with a 1-year exchange program at the École Centrale Nantes in France with the major applied mathematics, statistics, and data science. So now his current research interests include resilient control synthesis, symbolic control, formal methods, and learning-based control of dynamical systems. So I'm excited to hear his talk today, which I think is based on an award-winning paper at ECC. So without any further ado, please take it away, Youssef.
Yeah, thank you, Akash. So I will present our work that is conducted jointly with Professor Antoine Girard from University Polytechnic. So the work is titled Symbolic Control, Unveiling Free Robustness Margins. So let's start by a motivation. So consider a dynamical system that is modeled here by this drawing. So we wanted this dynamical system to satisfy a complex specification. For example, we wanted this drone to go to region A, pick up an item there, and then go to region B and drop the item there. While if the battery of the drone is low, it should go to the charging point P and stay there for 2 hours. And all of this, the drone should choose the trajectories that does not go to this red region C. So it should avoid this region. So this is an example of a complex specification that our dynamical system should satisfy. But on top of that, we wanted the dynamical system to satisfy the specification and to be also robust to disturbances. And these disturbances can be the difference between the physical reality of the model and the mathematical model that we have constructed. And also it may be, for example, if we take the example of an autonomous car, it may be a bad weather, for example, rainy or a storm, or for example, a defected sensor, maybe a cyber attack. So we wanted our dynamical system to be robust against these disturbances and also to satisfy the complex specification. So here I will give some literature review on robustness. So let's work through this timeline of approaches. So first we see that Tabueda, Ringer, and Apeza, these works focus on robustness for trajectory that are close to disturbance-free. They essentially ask, how much can we deviate from ideal behavior and still maintain correctness? So the emphasis here is on small perturbations. Then there is Leo and Racing and Cayley that take a more structured approach by considering disturbance, by considering an upper bound on the disturbance. So they conservatively approximate the worst case reachable set, essentially drawing a safety margin around all possible behavior. This is useful when you have a known disturbance range. Then there is Bay in his true work introduces an important refinement. He considers disturbance that vary based on the current state and input. So not just a fixed bound, but one that depends on where you are in the system. So this allows for more precise but less conservative abstractions. Then more recently, Saoud introduces resilience metrics specifically for systems that works under temporal logic specification. But what we can notice in all of this existing work is that they assume a predefined set of disturbances. But in our work, we flip this out. So instead of starting with a disturbance and asking how to build an abstraction, we start with the system and its symbolic abstraction and ask what is the largest disturbance under which the abstraction remain valid. So to understand the main idea of the paper, I will first explain what is symbolic control. So here I will provide an overview of the steps needed to construct a symbolic controller. But first, let's consider this continuous discrete time dynamical system. So it is modeled by this function f. So you can consider the function f as a dynamics, for example, for an autonomous car, which is a standard example. So for the classical control, we go directly and synthesize a controller for this dynamical system, either using MPC or PID or some other techniques for controller synthesis. But for symbolic control, the first step is that we calculate an abstraction of our dynamical system. So we go from continuous to discrete. And to do that, we discretize the state of space and the state of input. And then we define a notion of discrete transition system. So from this, we construct a big automaton. And from this big automaton, we borrow techniques from formal methods so that we can synthesize controller for a given specification. So the main advantage of this formal methods is that they guarantee the correctness of the controller. So we have 100% proven that the controller is correct. And then we use the last step, which is the refinement. And this refinement is very crucial because it allows us to take the control that we have constructed for the discrete and use it for the continuous. Because the main objective at the end is to construct a controller for our continuous dynamical system. And to do that, we need a condition that is called alternating simulation relation. And this condition it ensures that the refinement conserves the correct by construction controller. So also the controller that is used in the continuous time, it is also correct by construction. So we have formal guarantees for the controller. So now I will explain what is abstraction and how we construct the abstraction. So let's consider this physical system that is modeled by X, which is the set of states. So X is this region. As you can see, this region is not necessarily convex. So one of the main advantages of symbolic control is that we can work with nonlinear dynamical system, as well as nonlinear state space, as well as nonlinear input space. So we don't have any constraint over the dynamics or the states that we are working on, the space that we are working on. So let's consider this X is our state space. So we discretize this region to this blue space that we see, and then we discretize it. Here we have used square discretization, but we can use any other type of discretization. So this is the first step. So we got this XD, which is the discrete state space. And then for the input space, the only thing we do is that we take a finite sample from the continuous input space. So we have this continuous input space and we take finite samples, and this will be our discrete input space, which we call UD. And then for the transition system in the discrete, we should satisfy the next condition. So for a state that that will be the successor of this state. For example, if we take this state, the state that will be the successor of this state, it should satisfy that the reachable set of this state should intersect with it. So we have, for example, here this discretization, which is the next state of here, is intersecting with the reachable state of this initial state. So this is formally defined by this relation. So for a state Q prime to be a successor of Q and V, this Q prime should intersect with the reachable set of Q and V with disturbance D, which means in other way that the intersection between the two is different from the empty space. So from here, we have defined what are the next state for example, if we take this yellow state, the next state are this one, and this one for this input. So what we do is that we calculate the same thing for any state, for all states and all inputs. So we iterate over the states and then over the inputs. And from this, we can construct a big automaton that represents our dynamical system in discrete world. So yeah, so after explaining what is the abstraction, we need to explain what is the alternating simulation relation. So the problem is, how do we know our abstraction accurately represents the original system? So that's where alternating simulation relation comes in. So first, for every abstract state, which is the first condition, there must be at least one concrete state that corresponds to it. So think of this as the abstraction it should be complete. So it doesn't contain any imaginary state that don't map back to something real in the concrete system. And second, and this is the more complex condition, is when we have a pair of related states and the abstract system takes some actions from the abstract state, then in the concrete system and for any possible successor that you call reach, there must exist a corresponding successor state in the abstract system that remains related. So when the concrete system makes a move, to summarize, when the concrete systems makes a move, the abstract system must be able to follow it. And why this matter? Because this relation guarantees that anything we do in the abstract world, like designing a controller or verifying a property, will also hold in the concrete system. It's a formal guarantee that our abstraction isn't losing critical behavior. So the alternating simulation relation gives us confidence that analysis done on the abstraction world applies to the complex reality world. So now I will explain the main idea of the paper and how we got the idea. So let's consider this simple setup where we have, this is our state space, discrete state space. So the first thing is that for this discrete state Q1, we calculate the reachable set. So the reachable set is this white region, which I call here the closure of F bar. F bar is some sort of over approximation of F. So this is the reachable set of Q1, U1 with disturbance D. And this blue region is the union of the discrete successor of Q1, because as we can see, this discretization intersect with the reachable set, this one as well, this one, and this one. So the union of these four successor, the discrete successor region, are this region delimited by this blue margin. So if we construct the automaton of this transition, we will end up with this automaton. So we have Q1 with input U1 will give us the state Q5, Q6, Q8, and Q9. So what we have noticed is that if we add here a margin to this reachable set and calculate the corresponding abstraction here, we will end up with the same abstraction, because this white region plus the red boundaries have the same intersection with the same discrete state. So from here comes the idea that we have some free robustness margin while doing the abstraction. So after that, we have looked for what is the maximal robustness margin we can add to every to every reachable state of state and input while having the same symbolic abstraction. So from here comes the idea of free robustness margin that we have. So the first thing to do now is to formally define this maximal robustness margin. So for that, we have defined this map, which we call epsilon max, which goes from the discrete state space and the discrete input space to the positive real number, and which represents the maximum robustness margin of QU in these spaces. So it is defined by this quantity. So this quantity is simply, we are looking for the maximal epsilon, just that the reachable set of Q and U plus a ball of radius epsilon should remain inside the discrete successor of Q and U. So here in this graph, we can see it clearly. So we are looking for the maximal margin, which is the red margin, that if we add it to the reachable set, which is this quantity, which represents the white region, it should remain inside this blue region. So now we have defined this robustness margin, but we have defined it in the discrete world. So we need to transform it to the continuous world. So to do that, we define a quantizer that assign for each state X, which is a continuous state, to its corresponding symbolic state Q. So from this, we can define a continuous map, epsilon max, that is working on the continuous space X and represents the maximum robustness margin for any X and U in X and UD. So this epsilon max is defined by the same definition, but the only difference here is that here instead of writing X, we write Q of X, which is the symbolic state of X. And the same thing here in the discrete transition relation. So after giving the formal definition of robustness margin, we have proven three key properties. So let's consider a relation defined by if X and Q are related, only if we have X is belonging to Q. So the epsilon max we have defined is satisfying that for all state and input, it is always strictly positive. So this proves that we have all the time free robustness margin. The second property is that for any map that is lower than our maximal robustness margin, and this is for any state and input, the relation R is an alternating simulation relation between the discrete abstraction and the continuous perturbed system. So this gives an upper bound on the robustness margin that if we are working with perturbation less than the maximal perturbation we are working on, we guarantee that the alternating simulation relation is conserved. So for the third property, I need to explain what is delta over approximation. Then I will provide the key property. So what is a delta over approximation of F? So let's consider here the same example. We have this white region, which is the exact reachable set of Q1, U1 with disturbance D. So generally in control theory, it is very difficult to calculate the exact reachability. So we use some techniques of over approximations. So here we have used this interval, which is an interval in 2D that over approximates f, which we called f bar. So f bar is the over approximation of f. And then we have the white region plus the red region is the exact reachable set of Q1, U1, and D plus the ball of radius delta. So this f bar is a delta over approximation of f because f bar is included in f plus the ball of radius delta. This is the definition of a delta over approximation. So it is defined here mathematically that f bar should be contained in the exact reachable set plus the ball of radius delta. So if we have f bar is a delta over approximation of f, we have the next property. So this property says clearly that if we can find a state and an input such that there is a perturbation or a robustness margin epsilon bar, and this epsilon bar is bigger than epsilon max plus delta. If we only have one state and one input that satisfies this condition, which is bigger than our maximum robustness plus delta, so we no longer conserve the alternating simulation relation between the abstraction and the perturbed continuous system. And this gives us a measure of the tightness of our robustness margin. So here I will summarize what we have done, and I will explain how with this configuration we can synthesize robust controller. So first we begin with a discrete-time dynamical system, and we construct a symbolic abstraction. Then we have an alternating simulation relation between the two systems, and with this alternating simulation relation condition, we can guarantee that if we synthesize a controller for the abstraction, we can refine it back to our continuous system. So this is the standard way of doing symbolic control. Now we consider a perturbed system, which is near to the reality of physical reality of models. So for this perturbed system, we have one condition. If this epsilon that we have used here, this perturbation, is lower than the maximal robustness margin we have defined, so we guarantee that as well we have the alternating simulation relation between the same symbolic abstraction, so we don't need to recalculate the symbolic abstraction. And the second thing is that the same controller that are synthesized for the abstraction can be refined back to this perturbed system. And this gives us some robust controller synthesis. So these controllers can be robust to these perturbations. So for the numerical result, we have two case studies. So the first one is a double integrator, which have two states. So the first is the position and the second is the velocity. And then we have a control input U, and then disturbance D1 and D2. And for the sampling period, we have used a tau equal to 0.15 seconds. So the specification we wanted this dynamical system to satisfy is that we want it to remain all the time inside this region, which is defined by 0.6 times -6 and 6. So here we have this heat map where the colored region corresponds to our safety controller. So this is the safety domain that the controller computes. And then we have, so for the x-axis, we have x1, and for the second y-axis, we have x2. And here we have the gradient of the level of the robustness we have here the input value we can apply at each discretization. So here we have plotted as well 3 trajectories. The first one, which is the blue one, is the nominal trajectory. So it is the dynamical system without any disturbance. So we can see that the blue trajectory remains inside this colored region, which means that we satisfied the specification. The second trajectory is the red one, and we can see as well that it satisfied the specification because it remains inside the colored region. But for this green trajectory, we can see that after 5 time steps, it goes beyond the colored region because we have applied a perturbation that is bigger than the maximal robustness margin we have defined. So this clearly shows that the robustness margin we have defined is a tight bound. So for the second example, we worked on a differential drive mobile robot defined by this dynamical system where we have the position x and y, x1 and x2, and then we have an angle, which is the orientation x3, and then we have disturbance and the sampling period, which is equal to 1 second. And then we have linear and angular velocities that are the inputs, so u1 and u1. So here in this setup, we have this complex specification. So we wanted to reach either R1 or R2, but only one of them, and then reach R4 while avoiding, and then reach R3 while avoiding the red region R4. So we have picked 2 starting points. So from this point, we have the dynamical system goes to R1 and then goes to E3. And then from this starting point, it goes to R2 and then goes to R3, which means that we have satisfied the specification. But on top of that, we can see that even if we add disturbance, which corresponds to this green trajectory, the specification remains satisfied, which proves that the theoretical results we have found are consistent. So here are some numerical values. So for the lower band of the robustness margin, it is 0.01. And for the upper bound, it's 0.72. And the mean of the robustness margin is 0.036. Then for the conclusion, we have 3 key contributions in this paper. Is that the first is that we have proven that symbolic controller are inherently equipped with free robustness margin. And we have proven that they all the time exist because the epsilon max we have defined is all the time positive. So we all the time have this free robustness margin that we can make advantage of. The second thing is that we have characterized the largest robustness margin that preserves the alternating simulation relation between the abstract and the and the continuous perturbed model. And the third thing is that we can refine correct by construction controller from the disturbance-free symbolic abstraction to a perturbed version of the original system. And this for any specification, because the alternating simulation relation ensures that any specification that is synthesized for the abstraction, it can be refined back to the continuous continuous system. So the last thing is that this paper has gotten a finalist for the Best Student Paper Award in the European Control Conference. So thank you for your attention, and you are free to ask any question.
Okay, thank you for the great talk, Youssef. Do we have any questions from the audience? Looks like we have one from Brendan in the chat. So he's asking, do you have any ideas for how to extend this technique to systems that evolve continuously in time? Or is it sufficient to approximate them with a very small time step despite the additional conservatism each time the true reachable set is over-approximated with abstract states?
Yeah, normally what we have done is that we have created a perturbation for the symbolic model. But the idea is that this robustness margin that we have created for the symbolic, which is the discrete world, we apply it in the continuous world. So this robustness margin, normally it is used for the continuous world, not for the discrete world. So yeah, so this robustness margin can be applied directly to the continuous world.
I think it might be relating to like a continuous time evolving system. I think you had a
Okay.
time system, right?
I think for the continuous time dynamical system, we should look at how we can do the symbolic controller for this, and I think it should be as well something that can be done. Yeah.
Cool. I had a question about, so you had a disturbance lowercase d to the dynamics f.
Mhm.
So that is that disturbance different than the additive ball you added for the actual stability margin? So those are
Yeah,
two,
yeah,
okay. Is there
yeah.
like a
It's
way?
it's a yeah, it's a different disturbance. So we can benefit from both of them. Let's, for example, take a yeah. Yeah, here, for example, we have this disturbance dk, and this disturbance is modeled inside the symbolic abstraction. So when we are constructing our symbolic abstraction, we take into account this disturbance, and then we can as well add more disturbance that is related to the construction of the abstraction.
Got it. So this DK is sort of the mismatch between the true system dynamics and
Mhm.
our mathematical model, I guess.
Yeah.
And then the epsilon ball later is sort of the stability margin associated to the abstraction that you've chosen, basically.
Yeah, it's like a perturbation over the evolution of the system. So, for example, if we have some external perturbation, for example, for an autonomous car or something like that, we can have this flexibility if we can calculate this perturbation.
Got it. Okay. And then my, I guess, follow-up question is, so for these sort of abstraction-based approaches that need to grid the state space, is that something that can be like very efficiently done for high dimensional systems, or do you need to like sort of maybe use some lower dimensional model to sort of help bridge that gap?
Yeah, yeah. One of the main bottleneck for the symbolic abstraction is the time of computing of all of the state and input transition system relation. But there are some efficient algorithm that works on polynomial complexities, and some of them we can reach even linear complexity. So it is nearly linear on the number of the discretization that we will do on our system.
Got it. Thank you. Any other questions from the audience? Okay, I think with that, that will end the final seminar in this series.
Yeah,
Thank you,
thank you very
Youssef,
much.
for giving a fantastic talk today. And thank you to
Thank
all
you.
the speakers and all the previous sections as well. So thank you all for joining, and I hope to see you at CDC.
Yeah, see you.
All right.
Bye.